Let's say you're given this piecewise function, and in the Fourier series you have to find a1 and b2. You'll need the formula for the Fourier series, and because the interval is from -5 to 5, L is 5. And then we need a1 and b2, so I replaced n by 1 and 2. That leaves us with these two integrals, which should be straightforward in calculation. So let's do it. First, a1, you take the integral and you split into two intervals, because then you can say from -5 to 0, fx is same as 6x plus 3, and from 0 to 5, f of x is same as 2 minus 5x. It's important that you don't use even and odd arguments here, because the interval is not symmetric. If this was integrated from -5 to +5, then the interval is symmetric, and then you can say 6x is an odd function, cosine is an even function, multiply them, it's an odd function, so we can get rid of 6x altogether. But such an argument doesn't hold here, because the integral is from -5 to 0. That means you have to do the calculations honestly. Okay, so let's try that. Here we have the tabular integration for both of the integrals, and the tabular integration is computed this way. First, there's a differentiation column, and one of the factors are continuously differentiated until you hit 0, and the other function you integrate. And whenever you integrate the coefficient of x in here, you have to take that and put the reciprocal in front, so you get 5 over pi. Cosine integrates to sine. If you integrate again, sine integrates to negative cosine, and because another 5 over pi comes out, you get 25 over pi squared. Then the first column starts with plus and it alternates signs. Once you've done completing this table, then you have to know how to read off the conclusion of this tabular integration, and you do it like this. You multiply this way, okay? Here you're given a piecewise function, and you're being asked for some coefficients of the Fourier series. Now, from the formula for the Fourier series, our L should be 5, because the interval is from -5 to 5. And then, because you want a1 and b2, this n should be replaced by 1 and this one by 2. That leaves us with these two integrals, which should be quite straightforward to calculate. Let's start with a1. First, you want to split the integral into two, so that in the first interval, -5 to 0, you can replace fx by 6x plus 3, whereas in the second interval, you can replace fx by 2 minus 5x. Now, it's important that you don't use the argument using odd and even functions here. See, if the interval was from -5 to 5, then it's a symmetric interval, and therefore you can say, oh, if you multiply an odd by an even function, then it gives you an odd function, so integrating them over -5 to 5 will give you 0. However, such an argument doesn't work here, because this interval is from -5 to 0, and the interval is not symmetric. Only when you have a symmetric interval, you can talk about even and odd functions. That means we have to actually honestly evaluate these integrals. So I try to do that by drawing these two tables, and the tables here are constructed as follows. First, one part of it is differentiated. 6x plus 3 differentiates to 6, and then you differentiate that to get 0. The other one is integrated, and whenever you integrate, this coefficient of x should be brought forward as a reciprocal, so 5 over pi comes in front. Cosine integrates to sine. Integrating this again, you get negative cosine with another 5 over pi coming outside, so you get 25 over pi squared. And then the first column is the column of signs. You always start with plus, and then you get 0, you get negative, and then plus. It alternates, plus minus alternates. Okay, once you're done completing this table, then you have to read off the result of the integral, and the way you do it is by multiplying in this way. You go across and slightly tilt down. Same thing here. And multiplying these things and adding them will give you the result. And here you have to do the same thing. So this column is basically the same, but this derivative is different. And again, you multiply this way. Okay, so the result of the integral are these two functions. And now we can use these results to replace these integrals. And on top of that, I actually took the 1/5 and multiplied inside because they're both divisible by 5, right? So 5 divided by 5 gives you 1, whereas 150 divided by 5 is 30. And I did the same thing here as well. 5 divided by 5 is 1, and 125 divided by 5 is 25. Because this is a definite integral, you still have to plug in these two endpoints into the function and subtract. And when you do that, first notice that when you plug in 0, you get sine of 0, which is 0. And when you plug in negative 5 in here, you get sine of negative pi, which is 0 again. So that means this portion does not produce anything at all. On the other hand, the cosine, when you plug in 0, you get cosine 0 as 1. And when you plug in negative 5 and 5 cancels to give you negative 1, so you get cosine of negative pi, which is negative 1. You can do the same thing over here. Sine will again give you 0. On the other hand, when you plug in 5, you get cosine of pi, which is negative 1. When you plug in 0, you get cosine of 0, which is positive 1. So using all those results, you can compute. As you can see, when you plug in 0, you get 1, and when you plug in negative 5, you get negative 1. On the other hand, here, you plug in 5, you get negative 1 first, and then when you plug in 0, you get positive 1 later. So be careful. The negative 1 in the first integral happens in the second term. Negative 1 in the second integral happens in the first one. Okay, and then you can see that this is 30 plus 30, so it's 60 over pi squared, and this is positive 25 plus another 25, that's 50. 60 plus 50 is 110, so that's the result of A1. Now for B2, you basically the same argument. You also write down the tables for the tabular integration, and if you read off the result, you get these. It's done exactly the same manner. Probably the only difference is because the coefficient is 2 pi over 5. When you take the reciprocal, you get 2 here, and then another 4. And then instead of cosine, sine, cosine, this time is sine, cosine, sine. Okay. So this is the result of the tabular integration. Now we replace the integrals, and we have these two definite integrals to compute. You again have to plug in 0 and negative 5, but the sign terms produce 0 for the same reason. And when you plug in 0, it's 1. When you plug in negative 5, it's negative 1. Same thing when you plug in 5. Oh, no, this time, when you plug in negative 5, it's cosine of negative 2 pi, right? In that case, it's 1, okay? Cosine of 2 pi is 1. Cosine of negative 2 pi is 1. So this time, in both cases, you get 1s. But also, these numbers change, too. So what happens is that when you plug in 0, it's just 3. And then cosine gives you 1. And then when you plug in negative 5, it's 6 times negative 5 plus 3, and then cosine gives you 1. And then the same thing can be done for the second part. When you plug in 5, it's cosine 2 pi, which is 1. But when you plug in 5 here, it's 2 minus 5 times 5, or negative 23 here, okay? And then you just have 2 and then 1. So you do this calculation, and finally simplify, you get negative 5 over 2 pi. So those two numbers are the answers.